Continue with our study of thermodynamics by discussing the first law of thermodynamics. The first law of thermodynamics is actually a statement of the conservation of energy. Well, how does conservation of energy play in thermodynamics? Well, what is heat? Heat is a form of energy. Now, when you supply heat to an object, now particularly let's talk about gases. If you heat a certain amount of gas, have you experienced that the amount of gas will expand? When you drive your car for some time, the air inside the tire gets very hot and the hot air expands. You see, the pressure, the tire pressure increases as a result of that. Now, when you boil water with a lid on top of the container, when the water begins to boil, the lid begins to move up and down. Why? Because the steam, which is a gas, expands, and the expanding gas can do work. Now, what does this mean? It means heat can be converted to work. Well, heat is a form of energy which can be made to do work, and work will in turn be converted to heat. Now, there is an equivalency. Conservation of energy is satisfied in these conversions, and the first law of thermodynamics actually deals with the relationship between work and heat. Now, the first law of thermodynamics is a statement of the law of conservation of energy, which describes the behavior of systems when heat is either added or removed from the system. Now, heat added to a system can result in two things. What are the two things that heat can do to a system? We have talked about at least one of them. Heat added to a system can increase the internal energy of the system. Is that right? So it increases the internal energy of the system. We will use U for the internal energy, and therefore delta U will represent the change in the internal energy. A certain amount of heat supplied to a certain amount of gas will increase its internal energy. It also results in the system doing work. We will represent W for work, and delta W will be the change in the amount of work. So, when heat is added to a system, that can increase the internal energy, and also it can result in the system expanding. When the system expands, it does work. So these are the two things that heat added to a system can do. If delta Q is the quantity of heat added to a system, then we can say this delta Q results in an increase in internal energy delta U and a change in the system doing work delta W. That means this delta Q equal to delta U plus delta W. Now, this is the statement of the first law of thermodynamics. In other words, it is a statement of the conservation of energy. The total amount of heat added is a measure of the increase in the internal energy plus the work done by the system. Now, this statement of the first law of thermodynamics establishes a direct relationship between heat and mechanical work. You see, the Industrial Revolution actually started when scientists established this relationship, the relation between heat and work. You see, a lot of mechanical work that we can now get heat to do for us. We drive an internal combustion engine. It is a heat engine. Heat doing work for us. steam engine which was discovered by Stephenson long time ago. Actually, he observed the movement of the lid of a cooking pot as the water was boiling. Then he said, if steam produced by boiling water can do this work, we can put it to good use. And that is the evolution of the locomotives. You see how our lives can be made easy. We moved from the horse and cart era into the time of trains and cars and so on because of this, a relationship between heat and mechanical work. And so you can see the part played by the first law of thermodynamics in our lives is enormous. Now, this statement suggests that mechanical energy can be converted to work and vice versa. Work done will produce heat, and heat can produce work. One can be converted from one form to another. While W is a measure of the work done by the system, when you supply heat to an object, W represents the work done by the system. Negative W is a measure of the work done on the system. Now, what is an example of work done on the system? Work done on the system can result in heat generated. Now, have you ever used a pump, a bicycle pump? As you keep pumping, what you are doing is you are doing work on the gas. You see? And if you are holding the barrel, you can see the barrel gets very hot. The work done on the gas becomes heat. So, one more time, if work done by the gas is positive W, then work done on the gas will be negative W. I want you to distinguish there. The internal energy U is a function of the state of the system. We have been talking about the three different states of the system: pressure, volume, and temperature. In fact, internal energy is actually determined by these states of the system: pressure, volume, and temperature. In fact, you can add the internal energy along with this so that the state of the system is now described by pressure, volume, temperature, and internal energy. So when a gas is compressed, if you compress a gas, its pressure will change, its volume will change, its temperature will change, its internal energy will change. In the same way, if you allow a gas to expand, its pressure will change, its volume will change, its temperature will change, and its internal energy will change. So all these four are connected together. They are now the states of the system. Now, for a small quantity of heat dQ added to a system, the first law can now be written as dQ equal to du plus dW. This is the same equation. We earlier wrote delta Q equal to delta U plus delta W. You can write this using differentials. Remember, differential of a quantity is a small change in the value of that quantity. So dQ equal to du plus dW is the same statement of the first law of thermodynamics. Let's do a simple problem. If 1.68 times 10 to the 6 joules of heat energy is added to a gas that expands and does 800 joules of work, what is the change in the internal energy of the gas? Well, this is a direct application of the first law of thermodynamics. A certain amount of heat added will do two things. It increases the internal energy and it does work. Alright, so we've got delta Q or dQ is 1.68 times 10 to the 6 joules. That is the amount of heat added. dW, the work done on the system, is the work done by the system. Alright, dW equal to 8 times 10 to the 5. And we have dQ equal to du plus dW. So the system does 800 kilojoules of work. 800 kilojoules is 8 times 10 to the 5 joules. Now therefore, what is du equal to? du equal to dQ minus dW. That will be 1.68 times 10 to the 6 minus 8 times 10 to the 5. And that is 8.8 times 10 to the power 5 joules. So, of all this heat that is added, this much is made into useful work. The system does this much work, and the rest of the heat increases the internal energy, so that the first law of thermodynamics, the conservation of energy, is satisfied. Okay? Another example where mechanical energy can be converted to heat energy according to the law of conservation of energy. At Niagara Falls, the water drops 50 meters. If the change in potential energy goes into internal energy of water. Now remember, internal energy can be increase in potential energy or kinetic energy. Here we assume that all that potential energy goes into increasing the internal kinetic energy of the molecules of the water. That means it contributes to an increase in temperature. Only an increase in kinetic energy will contribute an increase in temperature. Alright, compute the increase in its temperature. Alright, let's consider m kilogram of water at the top of the fall. Well, I have to apologize for the shoddy diagram of the Niagara Falls that I have drawn here. Alright, we start with m kilograms of water at the top. What is the potential energy of that m kilogram of water? Its potential energy U equal to mgh. Well, so the potential energy at the top is mgh. And when it falls down all the way through 50 meters, all its potential energy will be lost. All that potential energy will become kinetic energy, or it becomes internal energy of the molecules of water. Potential energy at the bottom is 0. Therefore, the change in energy, what is the change in energy as the water reaches the bottom? Will be delta U equal to mgh. Because it started with a total energy of mgh. At the bottom, its potential energy is 0. So, the change in energy, therefore, is mgh. Now, this change in energy becomes internal heat energy. Therefore, if delta theta is the change in temperature of water, let me see if anybody remembers that. Now, if m kilogram of a substance undergoes a change in temperature of delta theta, what is the amount of heat added to the system? What amount of heat added to the system will result in a change in temperature of delta theta for a mass m if the specific heat of the system is C? Can you recall that? dQ, the amount of heat added to result in a change in temperature, will be mass times specific heat times change in temperature. And we will assume that all this dQ comes from that change in energy mgh. So this is now set equal to mgh. And therefore, we can now solve for delta theta. You can see mass and mass will cancel from either side. So that will not feature in the problem. Therefore, delta theta equal to GH divided by specific heat of water. G is 9.8, H is 50 meter, H is 50 meter, and of course the specific heat of water is 4180, and that will be 0.12 Kelvin. As the water falls through a height of 50 meter, its temperature will increase by 0.12 Kelvin. You see, a direct consequence of the first law of thermodynamics. Another problem. A lead bullet, initially at 30 degrees Celsius, just melts upon striking a target. Assuming that all of the initial kinetic energy of the bullet goes into the internal energy of the bullet to raise its temperature and melt it. Can you believe that it will happen? Yes? The bullet that is moving with a tremendous velocity strikes a target, and all the kinetic energy it was carrying is now used to increase the internal energy of the bullet, which then increases its temperature and melts it. Alright? What are we supposed to find? Calculate the speed of the bullet upon impact. We have the melting point of lead is 327 degrees Celsius. Latent heat of fusion for lead is 2.47 times 10 to the 4 joules per kilogram, and specific heat of lead is 128 joules per kilogram per Kelvin. Alright, now how do we apply the law of conservation of energy, or the first law of thermodynamics here? Well, the moving bullet has a kinetic energy. What is the kinetic energy of the bullet that has a mass m and a speed v? It'll be 1/2 mv squared. And all that energy is going to become a quantity of heat. And what is that quantity of heat going to do? That quantity of heat, first of all, increases the temperature of the bullet from 37 degrees to 327 degrees. Now tell me, what is the amount of heat needed to do that? To increase the temperature of the lead bullet from 30 degrees Celsius to 327 degrees Celsius. It will be mass times specific heat times change in temperature. Now, is that all? No. After increasing the temperature to 327 degrees Celsius, it is then converted from solid to liquid lead at the same temperature. There's a change of state. The amount of heat used to do that will be mass times latent heat of fusion. That means, you can see I'm doing this problem in mind, and you must actually practice doing this kind of thinking. All the energy that the bullet carried, 1/2 mv squared, has become internal heat energy, and that heat energy is used in two ways. First, mc delta theta to increase the temperature from 30 degrees to 327, plus mlf, mass times latent heat of fusion, to convert lead from solid to liquid. All right, let's write these things down. Let the speed of the bullet be v and its mass be m. The kinetic energy K upon impact then will be K equal to 1/2 mv squared. All right? This energy is used. All this energy is used to increase the internal energy. So all this has now become heat. Raise the temperature of the bullet to its melting point of 327 degrees and then melt it. Alright, we have all this data which we can use for that problem. That means 1/2 mv squared, that is the total quantity of heat. All that mechanical energy is now converted to heat. And that heat is used to increase the temperature of the bullet. Mass times specific heat times change in temperature, plus change the lead from solid to liquid without changing its temperature. Mass times latent heat of fusion. And you notice mass will cancel from everywhere. You don't need the mass of the bullet to do this problem. Alright? That means 1/2 v squared equal to specific heat of lead is 128 and delta theta is 327 minus 30 plus latent heat of fusion is given to be 2.47 times 10 to the 4th. Notice again that the mass has cancelled from each term. And now the only unknown quantity is V. You can solve for that. The right hand side simplifies to 62,716, and that is 1/2 v squared. Therefore v squared is double this, and therefore v is the square root of that, and that is 354 meter per second. Okay, let's do another one. A small immersion heater is rated 550 watt. Now, what is a watt? A watt means joules per second. You have done that in Physics 1, the unit of power. So what is the meaning that an immersion heater is rated 550 watt? It means that immersion heater will produce 550 joules of heat energy every second. That's the meaning there. It produces 550 joules of heat energy every second. Now what's the question? How long will it take to heat 200 grams of water from 20 degrees Celsius to 100 degrees Celsius, assuming that 90% of the heat produced by the heater is used in heating water? Alright, how do we start this problem? Since we need to find the length of time it takes to do this heating, let's start by saying that let the time be t. But first understand the meaning of the given statement. The heater is rated at 550 watt means that it supplies 550 joules of energy, which is heat energy here, to the water every second. Let the time taken to heat the water be t seconds. Alright? If 550 joules of energy are produced in 1 second, what is the amount of heat energy produced in t seconds? It will be 550 times t. Is that right? So the amount of heat energy supplied by the heater is 550 t joules. Now, are all this amount gone to heating water? No. Only 90% of this is used in heating water. The rest is lost to the surroundings. Well, there are many ways heat can get lost to the surroundings. Now, does it mean that the conservation of energy is not obeyed? Well, it is obeyed. All that heat is taken into account. Alright, 90% of this heat is used in heating water, and therefore the amount of heat Q used in heating water is 90% of this, which is 0.9 multiplied by 550 T. That will be 495 T. Now this is the amount of heat supplied to water. Now this heat is used by water to increase its temperature from 20 degrees Celsius to 100 degrees Celsius. Now what is the formula for the amount of heat used in raising the temperature by an amount delta theta? It is mc delta theta. So this quantity will be equal to mc delta theta, where m is 200 gram, c is the specific heat of water we know, delta theta is 100 minus 20. Alright, so the amount of heat energy needed to heat 200 gram of water from 20 degrees Celsius to 100 degrees Celsius is Q equal to mc delta theta. And that will be, mass is 0.2 kilogram, specific heat of water is 4180 joules per kilogram per Kelvin, and the change in temperature is 80 Kelvin, and that will be 66,880 joules. And what is this equal to? Where does this come from? From this quantity. So 495 T equal to this quantity, and therefore T equal to 135 seconds, that is 2.15 minutes. Okay, you must be very thorough with these kind of problems. Alright, let's now talk about internal energy of an ideal gas. We have been discussing ideal gas for some time. Internal energy of an ideal gas. Now, let me see if you remember, in lesson 2.1, we obtained an expression for the kinetic energy K of n moles of an ideal gas. Now remember, we obtained that using the assumptions that we made in that lesson. You remember we made 4 assumptions of the kinetic theory for gases. And using that assumption, we obtained an expression for the kinetic energy K of n moles of an ideal gas. Now, how many of you remember that relation? K equal to 3 over 2 nRT. Is that right? Yes. K equal to 3 over 2 nRT. In fact, when there is no change in potential energy, and that is the case in the case of a certain amount of gas. You see, when you supply heat to a gas, the increase in internal energy is purely increase in the translational energy of its molecules. So all the internal energy increase is translational energy or the kinetic energy, which results in an increase in temperature. So the internal energy of n moles of a gas at a temperature T is K equal to 3 over 2 nRT. Remember, this is a theoretical value. We can now subject that to experimental scrutiny to make sure that we are in the right track. So we will use this as we go on. For an ideal gas at low density, its internal energy depends only on the temperature, right? Its internal energy depends only on the temperature. This is because at low densities, the intermolecular forces can be neglected. At low densities, gas molecules are completely free. There is no potential energy at all. Now, thus the internal energy of a gas is just the translational kinetic energy of its molecules, given by U equal to 3 over 2 nRT. In other words, the internal energy, all the internal energy is due to the internal kinetic energy, and therefore the internal energy U equal to 3 over 2 nRT. You cannot forget that. I'm going to ask you that again and again as we go on. Let's now talk about work and the PV diagram for a gas. Work and the PV diagram. Now, do you remember in Physics 1 when we talked about work done by force? We said work done by a force is the area under the force displacement graph or force displacement diagram. Well, I'm sure you remember that, because work done is force multiplied by displacement. And if force does not remain a constant, then work done can be measured as the area enclosed by the graph of force against the displacement. In the same way, we can relate work done by a gas related to the pressure against volume graph or pressure against volume diagram. Now the figure on the right shows an ideal gas enclosed in a cylinder with a tightly fitting piston. Alright? The pressure of the gas, this is the gas inside, this is the piston. The piston can move back and forth. Now, the pressure of the gas is P and the volume is V. And the area of the piston is A. Now, if the pressure is P and if the area of the piston is A, what is the total force pushing the piston outward? That F will be equal to pressure multiplied by area. Is that right? The thrust, the total force is pressure multiplied by the area. So if the area of the piston is A, the force exerted by the gas on the piston will be F equal to P times A. And now, if this F displaces the piston through a small distance dx, what is the work done by that force? If the piston moves through a small distance dx, then the work done dW is given by dW equal to force multiplied by the displacement. Is that right? Work done is force multiplied by the displacement. So the force is P times A. Now I hope you can understand that concept, that the piston has an area A and the total force on the piston is P times A. Now consider this as the piston. You see, doesn't it look like a piston? And this is the area A. The pressure on it is P. So the total force on this area is pressure multiplied by the area. And if that force produces a small displacement dx, then the work done will be that force multiplied by dx. Alright. Now, that can be written as P times the, now, force is P times A. So I'm going to replace this force by P times A. And you notice I colored that A times dx. A times dx. Suppose this is A and this is dx. What is A multiplied by dx give you? If you notice, this is a disk. The face area multiplied by the thickness will be the volume. But in this case, what happened is that piston is moving through a small distance dx. That means A times dx here is the increase in volume. Is that right? A times dx is the increase in volume over here. This is A times dx, and that is equal to dV, the change in volume. Therefore, we can say the small work done equal to PdV. You see, when this force produces a small displacement dx on the piston, the work done during that time is pressure times the change in volume. Always remember, work is done only when the volume changes, because there has been a displacement. Now, the total work done when the volume changes from V1 to V2, if the initial volume is V1 and the final volume is V2, then the total work done will be given by an integral. Why do we have to integrate? Because as the volume increases, the pressure will change, the force will change. The force does not remain a constant. And that is why we got to go in very small steps of displacement dx. And then we integrate this whole quantity from V equal to V1 to V equal to V2. So the total work done is now given by integral V1 to V2 PdV. A very important relation, we would want to use it again. So the small work done when the displacement is very small is PdV, where dV is the change in volume. And if the volume changes from a value V1 to V2, the total work done will be W equal to integral V1 to V2 of PdV. And remember, integral is a measure of the area under the graph. So we will now look at that as we go on. Let's now talk about what is called an isobaric process. Now, do you remember when you talked about Boyle's law? We said Boyle's law describes an isothermal process. You recall that? What is an isothermal process? An isothermal process is a process where the temperature remains a constant. What is an isobaric process? An isobaric process is a process where the pressure remains a constant. In an isobaric process, the pressure remains a constant. So in that case, we can represent it like this. The pressure does not change. When volume changes from V1 to V2, the pressure does not change. And this makes it easy for us to calculate the work done. And the work done in this process, because the pressure does not change, the area is now a rectangle. You don't really need an integration in this case. The work done here, W equal to integral V1 to V2 of PdV. Remember, integral of PdV is a measure of the area under the graph of pressure against volume. You understand that, isn't it? So this is a graph of pressure against volume, and pressure remains a constant. That means this is the area that represents the work done. So since pressure is a constant, we can take that out of the integral. That becomes pressure times integral V1 to V2 of dV. What is integral of dV? Integral of dV is V. So that will be P times V. Lower limit is V1, the upper limit is V2. And you know how to do these kind of things. It will be P times V2 minus V1. Replace V by the upper limit minus replace V by the lower limit. You can see work done is P times V2 minus V1. If you look at the diagram here, P is a constant, that is your P. P times V2 minus V1 is the area of this rectangle. This is P and this is V2 minus V1. Therefore, this is a measure of the area under the PV diagram. So work done by a system can be obtained as the area under the PV diagram. It's a very important relation. I want you to remember these relationships. All right. The total work done when volume changes from V1 to V2 at constant pressure is W equal to P times V2 minus V1. Now, in an isobaric process, pressure remains a constant, and this is the process that we have just talked about. So W isobaric, work done for an isobaric process is P times V2 minus V1. Reinforce that idea one more time. Now, okay. Now, pressure volume, that is PV diagrams, are primary visualization tool for the study of heat engines. Now, as I told you, you come to school and back or go many places, carry with you a heat engine. Your car has a heat engine, internal combustion engine, and the study of such engines can be made easy by looking at the PV diagram of the engine. Now, here I have a PV diagram. Now you notice the stages 1, 2, 3, 4, 1. Now, this actually summarizes the complete working of the engine of your car. Now, do you know really how the engine of a car works? Now, let me take a minute and try and see if I can explain that to you. Now, your car engine has, I'm just going to take one cylinder. There's a cylinder, there is a piston, and the piston is, of course, connected to the crankshaft. Now, to make your engine start, in order to start the engine, you need to supply some extra external energy, and that is what the battery is for. So, when your battery first starts your car, the piston is pulled back. When the piston is pulled back, a valve will open and fuel will spray. Fuel, of course, mixture of fuel and air will spray into the cylinder. And then, when the mixture has been sprayed, then the piston goes forward. So the first stage is called the charging stroke. The engine is charged. What is the second stage? In the second stage, the piston is pushed forward, compressing the gas. You see, this is where the compression takes place. That means the gas inside is compressed to a very small volume. What will happen? The pressure and the temperature increases. So this is called the compression stroke. The second stage is the compression. And now what happens? At this particular time, your engine will produce a spark. Now, when a spark is produced into this compressed fuel and air, which is at a very high temperature and pressure, it explodes. And that explosion, that is the first time your engine comes to life. It is that explosion that produces that energy. So, you have the third stage. The third stage of the working of the car will be that big explosion in there, which will throw the piston backward. The piston is thrown back with that explosion. And finally, when the piston is pushed forward, all the spent materials are taken out. That is the exhaust. So these are the four stages. The third stage is called the working stage, and the fourth one is called the exhaust. So what happens? Heat is added. First of all, you have work done on the gas. This is, can you recognize this stage? The piston pushes the gas forward. Work is done on the gas. You can see that is given by the area below. This is a PV diagram. So if this stage is work done on the gas, that is this stage when the piston is pushed forward, given by this area. Then heat is added. How is heat added? The spark plug explodes. Once the spark plug produces a spark, there is a great explosion. Heat is added at constant volume. And then what happens? That great energy, the work is done by the gas. What happens? The piston is pulled back. The volume increases. The pressure decreases. This is the time when your engine does useful work. Isn't it? Yes, the engine does useful work given by the area under the graph there. Now that means, let me go back and show this one more time. Now, if this is the work done on the gas, I'm using the blue lines to represent that, then this will be the work done by the gas. You see that? The work done on the gas is the blue area. Work done by the gas is the red area. Therefore, what is the useful work done? It's the difference between the two, and that is the area shaded. So during this 4 cycle, the useful work done by your car engine is this. Okay, let's move on. So since the engines usually involve a gas as a working substance, the ideal gas law relates to the PV diagram to the temperature, so that 3 essential state variables for the gas can be tracked through the 4 cycles of the engine. I gave you the 4 cycles. You see that? You got the charging stroke, the compression stroke, the heat added, then the working stroke, and then the exhaust stroke. Since work is done only when the volume of the gas changes, look at this, work is done at 2 stages. Work done on the gas, the volume changes. Work done by the gas, the volume changes. These are the only stages when the work is done. Remember, work is PDV. When there is no volume change at this stage and at this stage, there is no work done. Alright, let's see if I can give you an illustration. If your car is a 4-cylinder engine like mine, it will sort of work like this. Now look at the 4 cylinders. Let's concentrate on 1 cylinder and look at the 4 different strokes. What are the 4 strokes I gave you? First is the intake stroke, taking in the fuel, then the compression stroke, then the working stroke where the energy is produced, and then the exhaust stroke. Alright, here is the intake. Now here is the compression, this is the combustion working, and then the exhaust. You see? And if you notice, each of these cylinders will go through these 4 cycles one after the other, so that energy gets delivered. Remember, the useful energy gets delivered only on the combustion stroke, only when the yellow stroke. You see, useful energy here, useful energy here, useful energy here, and useful energy here. It is one after the other. That means useful energy is delivered to your crankshaft continuously because of the 4 engines working one stroke after the other. So one more time, the yellow is the useful stroke. There is useful followed by the useful energy. followed by combustion, followed by combustion. So each of these engines deliver energy to your engine at a continuous rate so that your car will run very smoothly. Now, if there is only one engine, how will your car run? It'll go chuk, chuk. Is that right? Okay, I don't think you want that. For each cylinder, the area enclosed by the cycle on the PV diagram is proportional to the work produced by the cycle. So energy is delivered to the engine one after the other by each of the cylinders. If you have an 8-cylinder car, you can see it gets much more energy. So a sports car should definitely have more than 4 cylinders. Well, I'm going to stop this part of the lesson here. I'm going to record a second part of what is this called? 2.3, I suppose, a little later. So I will see you for that a little later.